60 million years ago, the surface of North America was a place filled with plant and animal life, spurred on by the warm air and plentiful rainfall. A forest with abundant light gaps, scrubby bushes and trees, palm tree thickets, and regions of gingers, containing great numbers and variations of turtles, birds, lizards, small mammals, frogs, snakes, and the famed dinosaurs. The Denver Basin exhibits the tale of a world-long past, filled with volcanic activity, flowing streams, and indications of swamps. With evidence of the formation of the Colorado Front Range, the sediments attributed to the D1 formation tell the story of a vibrant and flourishing world, what would become the last evidence for such a world for millions of years afterward. Everything changed when the asteroid crashed into Chicxulub on the Yucatan Peninsula, and 80% of the species on Earth disappeared during a period of 24 hours to 2 years, including the dinosaurs and the flora and fauna with which they coexisted. Tsunamis and shock waves stripped away layers of topsoil throughout the regions surrounding the impact site. Ash thrown into the atmosphere blocked the sun for up to 2 years. Heat waves and wildfires sparked more death and destruction, and layers of materials thrown into the atmosphere rained back down to Earth as tektites and spherules, depositing the airborne target rock in layers across the globe. Little survived in the wake of such large-scale destruction, and the world seen after differed greatly from the world before. Since the discovery of the iridium anomaly by the Alvarezes in 1980, and the subsequent understandings of the bolide impact which rocked the Earth's ecosystems and led to such a drastic change in the Earth's long history, what has happened during and after the deaths of the dinosaurs has gripped our attentions for decades. Though the Earth directly after the impact eventually led to the world we see today, across much of North America it could have taken up to 10 million years for the disaster flora to give way to increased diversity of flora and fauna once more. However, this was not exactly the case at the site of the Castle Rock Rainforest. When it was discovered in 1994 by Stephen Wallace, the area itself was slated to become the site of a railroad grading improvement effort. During the beginning stages of their excavations, large fossil leaves, on the order of hundreds of square centimeters, with the largest being 1,280 square centimeters, began to be discovered. Wallace's efforts to bring attention to his finds eventually led to the instigation of a conservation excavation in order to remove and preserve the large diversity of flora discovered at this unusual site. A mere 1.8 million years after the impact, which so drastically altered the course of Earth's history, the diversity and types of leaves at the site of the Castle Rock Rainforest is unprecedented, and as such is able to contribute greatly to our understanding of the location and era, as well as how sections of the Earth rebounded from the mass extinction and in doing so, formed the beginnings of the world as we see it today.
Castle Rock site is diverse in its geology. At the top of the hill we have the Castle Rock conglomerate, which has rhyolite mixed in. This rhyolite came from a volcano that erupted 37 million years ago. The reason the Castle Rock rhyolite is mixed in with the conglomerate is because it was a river at one point, eroding the rhyolite and adding it in with the abundance of other rocks and sediment found in the conglomerate. The layer of rhyolite seen on other buttes in the surrounding area is still there. The other buttes were not eroded by this river because they were higher up on the banks. What you can see today is a 35 million year old Castle Rock conglomerate, which is the youngest sedimentary rock unit in the Denver Basin. Consists of large blocks of rhyolite, granite, quartzite, and tuff. The poorly sorted sediment and the rounded grain size of this section has led researchers to believe this area may once have been a river. Below the conglomerate we will find the D2, which is approximately 55 million years old. The D2 is arkose and has mostly quartz and small amounts of potassium feldspar. It is very poorly sorted and consists of subangular grains. This section of D2 is believed to be the product of laramide orogeny. As we transition between D2 and D1, we know that there is about 9 million years missing between the two, which suggests a significant amount of erosion occurred. At the bottom of the hill is the Castle Rock Rainforest at the top of the D1 stratigraphic section. Located along I-25, Castle Rock Rainforest is determined to have been deposited during the Paleocene epoch of the Cenozoic and has been dated at about 64 million years old. The site represents forest floor leaf litter which fell from the forest canopy and was subsequently buried. This indicates there was minimal transportation. Presence of large alluvial fans during the Paleocene suggests that orographic precipitation related to the Laramide orogeny may be part of the story at Castle Rock. As we move on to the actual excavation of the site, we will see the sedimentary layer houses one of the most diverse fossil leaf excavations in the western interior.
The excavation of the Castle Rock site, headed by Dr. Kirk Johnson, unearthed approximately 10,000 fossil leaf specimens, belonging to over 100 species, making it one of the most diverse excavations of leaf specimens in the western interior, with species ranging from conifers to fruits and ferns to 90 other species of broad-leaved flowering trees. The Castle Rock Rainforest site is located approximately 180 meters above the KT boundary, with fossil-bearing units spanning 150 meters of outcrop within a strata unit 20 to 35 centimeters thick. According to Ellis et al. 2003, 5 quarry excavations occurred at the site between the years of 1994 to 1999, which rewarded volunteers with unusually well-preserved, large leaves with smooth margins, drip tips, and high spatial heterogeneity deposits, which were between 3 and 20 times more species-rich than other Paleocene leaf localities throughout the western interior. These leaves excavated from the site were once leaf litter which fell to the forest floor 1.8 million years after the KT extinction event, and were abruptly covered by 25 centimeters of mud, successfully preserving not only the fossil imprint, but also the leaf cuticles themselves, which is the protective film covering the epidermis of the living leaf. This astounding level of preservation is merely one of the unique aspects of the Castle Rock Rainforest site itself. These characteristics beg the question, can the Castle Rock Rainforest truly be considered a tropical rainforest? Or is the term misleading when applied to the site? Extant tropical rainforests, as defined by Ellis et al. 2003, are generally attributed to low-latitude areas with high rainfall and equable temperature, dominated by angiosperm trees and vines, and have high species diversity and spatial heterogeneity. Many rainforest species exhibit large, thick leaves determined by measuring the space between primary and secondary veins, smooth leaf margins, and elongated drip tips, most likely in order to slip rainwater off the leaf more effectively, thereby preventing rotting and disease. Wolf et al. 1998 determined that larger overall leaf area could indicate wetter climates, which are more likely to be warmer, on account of the role which water vapor plays in maintaining atmospheric heat. Temperate forests, on the other hand, often display such low species diversity that the 4 most common morphotypes commonly represent up to 90% of leaf litter over tens of meters, which describes most other early Paleocene sites from similar regions. Johnson and Ellis, 2002, determined that of the species found at Castle Rock, 69% are entire margined, smooth all the way around the leaf, 39.5% of the 48 species that preserve intact apexes exhibit drip tips, and the average leaf size is 67 centimeters squared. The 10 most abundant morphotypes account for 60% of total flora recovered, which are dominated by woody dicots. Though the Castle Rock Rainforest site displays extraordinary variation in species preservation, there is a significant lack of insect damage, particularly insect mines, attributed to the remains. Modern-day observations attribute correlations between the diversity of insect herbivores within a particular ecosystem and the diversity of the plant species available within the same region. Nonetheless, this does not appear to be the case at the Castle Rock site. Instead, Wolf et al. 2006 found that the flora exhibited some of the lowest feeding diversity in their dataset, with only 2 insect mining examples on 2 separate host plants found within the Castle Rock samples, with no other form of insect damage visible. In comparison, the Paleocene site of Mexican Hat demonstrates insect mining damage on 2.6% of all leaves found at the site, more than twice the amount found at any other site of comparative age. Insect damage is a valuable tool for understanding how various levels of the food chain were affected by the extinction and subsequent return. The lack of widespread damage at the site of Castle Rock indicates that the destruction of the plants upon which many insect miners, which are highly specialized to their specific ecosystems and hosts, fed, heralded a destruction of the miners themselves, and which were slower to return here than other regionally connected sites due to varied ecological pressures and instabilities.
This early Paleocene landscape featured the Rocky Mountains to the west and the Gulf of Mexico, along with some remnants of the western interior seaway to the east. These 2 key features played a large role in the creation of the Castle Rock Rainforest. It's thought that storms would begin in the Gulf of Mexico and move westward until they hit the Rockies, at which point the air would be forced to rise, cool, and condense. This potentially caused the monsoonal seasonality, which produced large amounts of precipitation on the eastern side of the Rockies where the Castle Rock Rainforest was. Early Paleocene coal beds found in other basins east of the Rockies without similar deposits west of the Rockies supports the idea of a rain shadow type situation where the eastern side of the Rockies receives a significant amount of precipitation. Using the size and shape of the fossil leaves found at the Castle Rock site, it is estimated that this area receives approximately 225 centimeters or 88.5 inches of precipitation each year. Along with large amounts of precipitation and moisture in the air, this area had a very warm mean annual temperature. Using leaf margin analysis, it is estimated that the mean annual temperature for this region was about 22.2 degrees Celsius. Typically in areas with similar conditions, plant decay is a very rapid process. So how is it that these fossils are so abundant and well preserved? Ellis et al. Explains that most of the Castle Rock leaf fossils are preserved as leaf mats or well-defined leaf layers. These leaf layers actually form the contacts between the different units of this formation, and lack of scratches or abrasions on the leaves suggests that the leaves were buried in the exact spot that they grew. Along with the leaves, ripples have been found at these contacts, which means that there was a current during deposition. We also know that the leaf fossils are very well preserved, which implies that they were deposited in a lower energy environment. These clues point us to the direction of the most likely depositional event, which would be a series of overbanked floods. These overbanked floods would move slowly along the forest floor over a wide area and carry large amounts of sediments, perfect for keeping the leaves intact and preserving them. At the Castle Rock site, there are 3 distinct fossil mats which separate the units, suggesting 3 separate flood events. The third flood was an intense event. The top layer consists of much coarser sediments, suggesting higher energy deposition. Also, there are no tree trunks above this layer, which means there was an immense amount of energy associated with this flood. It is thought that in the early Paleocene, the Castle Rock area resembled the modern-day area of Manu, Peru. Both of these areas lie at the base of large mountain ranges, Castle Rock at the base of the Rockies and Manu at the base of the Andes. Using Manu as an example, we can see that these mountains have an orographic effect on precipitation, much like the Rockies had on the Castle Rock area in the early Paleocene. Along with the geographic similarities between these two areas, the annual precipitation in Manu is about 300 centimeters and the mean annual temperature is around 25 degrees Celsius. There are also similarities in leaf structure. Fossils found at the Castle Rock site have similar features to those found in the rainforests of Peru, such as large leaf size and drip tips.
Supporting evidence for the monsoonal seasonality hypothesis exists in the form of the occurrence of coal beds in 3 pairs of Rocky Mountain basins, including the Raton and San Juan basins in Colorado and New Mexico, the Denver and South Park basins in Colorado, and the Powder River and Bighorn basins in Wyoming. Johnson and Ellis, 2002, demonstrate that in each case, the eastern basin accumulated extensive Paleocene coal measures, while the western basin did not. In addition, though it has been observed that there were several rainforest floras near the mountains of the Denver basin, they contained moderate diversity when compared to the Castle Rock site, and the regression of the Cannibal Sea by 61 million years may explain the absence of similar Castle Rock-style rainforests later in the Paleocene. Another possible explanation for the lack of sites rivaling the Castle Rock rainforest could be that overbanked deposits often and reliably represent species of trees growing within 100 meters, while even well-sampled collections of channel or marginal channel depositions largely represent less than 50% of local flora. If the flooding which contributed to the overbanked deposits at the Castle Rock site did not extend any further than the site itself, then similarly well-preserved deposits will be hard to discern. Furthermore, a few morphotypes discovered through the Castle Rock excavations have relatives living in modern rainforests today, including members of the families Lauraceae and Elacoparcae, thereby further connecting the Castle Rock site to modern rainforest flora and climate. Overall, the site itself is unusual in its extraordinary preservation and the information it provides regarding the movement of the Earth from the fern spike of the disaster flora to the rich and vibrant world we see today.